Awesome. Okay. Welcome everybody. Thank you so much for coming. My name is Aditya Dutt, and today we are going to talk a little bit about simulation rescue line competition. Let me open my Zoom. Okay, cool. So a little bit about me. I'm a high school senior at the Edison Academy Magnet School, and I'm studying electrical engineering and computer science. So I competed in the 2019 and 2020 RoboCup Junior Rescue Line competitions. I've also been teaching simulation rescue line for the past year and a half or so. And I'm the founder of missiondice.org, which is an organization I founded in 2019 to teach kids about CAD and engineering using Tinkercad, which is an online free 3D modeling software. So that's been really cool. So a little bit about what simulation robotics is, in case people haven't heard of it. So it's basically it's a category of computer tools that's used to run realistic simulations of robots in various environments. And it has a lot of really strong benefits. First is that the softwares are repeatable and deterministic, which is a term that basically means that if you run the same simulation over and over again, you won't get different results. And the cool thing about that is, for example, if you're trying to develop a robot, you don't need to worry about any hardware issues that cause noise or anything. So in the software that we'll be using, you can turn off all the noise and make it so that every time you run your simulation, everything should have the same result. So you can test the same thing multiple times. Some other advantages, it's faster than the real world because using a graphics card or strong computer, you can run the simulation faster than if you actually put down the robot on a map somewhere. It's easily iterable, which kind of goes back to the whole deterministic thing, which is you can make a small change and quickly test it again, rather than with a physical robot having to take it, download the code, set everything up again, and hit and start the robot. You can just hit play again. You can test dangerous situations or edge cases safely. So a strong example of that. So NASA, I think this is a simulation of the Opportunity rover that went up a couple of years, quite a while ago. And so they definitely use simulation robotics to try to simulate how the rover would work in the Martian environment without obviously being able to be at Mars and test everything. And finally, it's cheaper. If something breaks, you don't need to try to rebuild the robot again. You can literally just reset the simulation and try again. You don't have to worry about parts breaking or anything like that. So today we'll be taking a look at the WeBox simulator. And the cool thing about it is that it's completely open source and free. So unlike other proprietary softwares that's used in the industry, this is really good for education and research, and some companies in the industry do use it as well. Okay. So now something else. Google Blockly is really cool. It's a library from Google that's used for building beginner-friendly block-based programming languages. So if anybody's ever used like Scratch or anything, it has a very similar interface. But Google, rather than it being a software, is a library that other developers can use in their projects. So what it does is it converts this block-based interface, like you can see in the bottom left picture here. We have repeat blocks and addition blocks and all that, to standard text-based programming languages like Python, JavaScript, Lua, and Dart. And something cool that Blockly does is it has the capability for creating custom blocks that you can see in the bottom right corner here. So we'll take a look at these blocks more specifically later, but we can see we have robotics specific blocks that we've added in, such as setting up motors or getting sensors and stuff like that. And Blockly provides a way for developers to convert that into custom Python code or JavaScript or other languages. Sorry, at any point, if anybody has any questions, please feel free to raise your hand or unmute yourself and ask, please. Thank you. So a little bit about the rescue line competition that we're going to be simulating. It's a sub-league of the whole RoboCup Junior competition, which in itself is a high school version of the college RoboCup, which is big robots playing soccer. So that's pretty cool. So this league is the physical version of it, which you can see in the bottom left here, is a fully autonomous robot that follows a black line. Along the line, there are some things that the robot has to traverse past. So we have green square intersections, that you can see in the bottom right. So these intersections tell the robot which way to turn, when otherwise it would be an ambiguous situation what the robot should do. There are obstacles in the way. You can see this like water bottle in the bottom left that the robot has to detect and go around. There's debris such as speed bumps or toothpicks. And finally, there are ramps and seesaws that the robot has to be built hardware-wise in such a way that it doesn't fall over or fail in some way. And so this competition is meant to be a model or a physical simulation, not a software simulation, a physical simulation for a rescue robot that can help with disaster environments. Okay, so now what we've done over the past couple of months or a year is being able to put everything together. So we have this whole workflow where robotics-focused custom blocks in the Google Blockly environment gets converted to Python code. And then this Python code is saved as what's called a controller. A controller in Weebots is basically a software that tells a robot how to act and how to interact with its environment. So again, so this Blockly block code gets converted into Python code, and then it gets saved as a controller for the Weebots robot. And this is really cool because it allows kids to use an advanced robotic simulator in a much simpler way using this block interface to learn about coding, engineering, and especially problem solving. So I have a short demo of so we ran this as a custom, like a contest internally within Storming Robots. And so this kid was very successful during his term here. And so this was his submission to our internal contest. And I think he was in like grade 5 or grade 6 or something. So it's really impressive. Okay, so I'll speed through most of it, but it gives me the option to. So we can see that, so we have this robot here, completely simulated, no realistic, there's no actual physical robot. So this robot, it can pass through the gaps, it can do all this, it detects the green squares. The green squares especially are pretty tricky to deal with, much harder than someone might think. But so you can see that his robot is traversing these environments. Speed this up a little bit more. So he's able to do these complex intersections and turns. We have a ramp coming up next, I believe. Yeah, we have a ramp here. So more intersections. His robot traverses the obstacle. And finally, it stops at. Oh, I'm really sorry. 1 second. 1 second. I think whoops. Okay, here. I'll go through this. Thank you so much for that. All right. Okay. I think we can see the video now. Yeah. Okay. Thank you. Okay, so I'll show some of the important parts of this again. So the robot is line tracing. So you can see that the robot has a couple of these sensors in the front of the robot. It can detect these green squares because it's a color sensor. So it knows which way to go. It can detect these gaps and go straight through them. We have a ramp coming up next here. Seesaw. So the robot had to be designed to make sure that it knows it can detect these ramps or that it won't fall off the ramps. So it can traverse past these obstacles. Goes through this obstacle twice actually. Yeah, and it stops on the red dot. Awesome. Okay. Okay, so I kind of wanted to give a short demo of how to get started with this. So the recording for this will be available online, so everybody can follow along later. But I did want to talk a little bit about how to do this. So the first link, actually, I'll put these links in the chat in case anybody wants them. Okay, so this first link is the dev.stormingrobots.com. So here we can see all the different cool stuff that all the developers of Storming Robots are doing. So if we want to go to the rescue line part of it, we can click this purple button here that says rescue line simulation. And so now we have some details about RCJ and the World Cup for this. And then we have some GitHub links that I'll put this in the chat, and how to install stuff. And we'll get some more resources and very detailed tutorial videos coming up very soon after this class. So some more links. Okay, so okay. So I believe, okay, cool. So so this is the download page for Weebox. So it's cyberrobotics.com. It's in the chat. Okay, cool. And so we have some download stuff. Welcome to CFP35. I don't know what that was. Okay, cool. So right. Okay, so Weebox. So the newest version is version 2023A, which just got released like last week or something. So the first thing to do is hit this download button. And so this download will give you an installer, which is very self-explanatory, actually. It's very easy to get started with. So it'll run you through the whole install process. And so once you do that, you will come to a screen that looks kind of like this. So I'll talk a little bit about the interface of how this Weebox works. And yeah, okay. So on the left side of the screen, we have what's called the scene tree. And the scene tree is where all the elements of your simulation are. So your worlds, all your maps, your line tiles, and your robot itself will all be visible in the scene tree. So in that scene tree, you'll be able to see their sensors and everything in that. Along the top is probably what's one of the most important parts of Weebox, is shows you how to interact with your simulation. So so we have a play button here that's used for starting and stopping the simulation. We have a step button, which is very helpful for just going through individual time steps. So so the way Weebox does its simulation is that I think the default is 32 milliseconds. It calculates the positions of everything in the world every 32 milliseconds. So you can step forward 32 milliseconds at a time to see exactly what your robot is doing each step of the way. You can reset your simulation here. You can run through your simulation much faster than normal, as long as your computer is powerful enough. And then there are some recording tools here so that you can record what your robot does, like we did, like I showed you in that demo. And then we can also reload our world. So I will show you what world we'll be working with today. It is this line 1 world. Cool. So okay, so you can see so this is very simple, just a normal line tracing world. We have our robot here, and we have a sensor you can see out here in the front. This is the color sensor, the light sensor. So just basic how to interface with this world. On the mouse, there's a right mouse button, and the right mouse button is used for panning around, or it's kind of like as if you're wiping around the screen and moving it around. If you just click and hold on the left mouse button, we can orbit around wherever we click. And finally, the most self-explanatory one is the zooming with just the scroll wheel. So okay. So this is the basic way to interface this. You can see the scene tree is a little bit more populated on the left side. We have a group of these tiles that make up the line map. We have the robot itself. And you can see that it has some properties like its translation, its position, the rotation, the scale of the object, the name of the object and everything. It also has children, so it has like sub-objects inside of it. So it has all the inbuilt distance sensors and the LEDs and stuff like that. And in here, you can see the actual color sensor. Okay. Okay. So let me show where we can get all these worlds and how to get started with Blockly. So stop share screen. Let me go to the link 1 second. Okay, so let me put this link in the chat. So here's the link in the chat. Let me share the block link. Okay. So if you click the link, you should show up in this GitHub. I added some new worlds and I ported the Blockly to 2022 because the last version made a pretty big change. So but this works for 2023 as well. So so to download this code, if you're familiar with GitHub, you can just you can clone this repository and get access to everything. And if you're kind of more new to GitHub, an easy way is to click on this green button here that says code, and then click download zip. So this will download a zip file of this branch for GitHub, and you can extract the zip file, and you should have a folder called I think called SR Blockly. So let me open that folder up and show you what it looks like. Screen. Awesome. Okay. So okay, cool. Okay, so if you open up this folder, you end up here. And so to find your way to the worlds, which is as a student, this is probably what you'd mostly interact with. There's a folder here called worlds inside here. And you can open up any of the worlds here to use. So today we'll be looking at line1.wbt, which is the very simple rescue line world. Okay. So now the question is, how do we open this Blockly interface and start writing code for this robot, right? So in all of the worlds in that world folder, there are two things that look like they're a robot. There's one that's labeled as Pioneer 3DX, and that is the actual physical robot that we'll be using. The other one is usually called something like robot or Blockly supervisor robot, and this is a separate way that is used for interfacing Weebots with the Python code, with the Blockly code that's written. So if you right-click on the Blockly supervisor robot and click Show Robot Window, it will open up in your browser a local page that has all your block code interface into it. Okay. So if anybody's familiar with Scratch, this environment probably looks very similar. So on the left side, we have a bunch of tabs like variables. You can create variables, functions. Blockly is really cool in that you can actually make functions, which makes it much easier to write code without everything being very messy. So we have standard function stuff. So these are some of the custom blocks that we added. So there's a motor category. So students can interface with robots, with the motors on the robots and set their velocity and get their encoder values. We have some time stuff, so you can delay, you can get the current timestamp of the world, reset the time, and you can also step your robot step by step through those 32 millisecond time steps I was talking about. We have sensors. So we have a couple of sensors in the Blockly world right now. We have a gyro sensor, which is very useful for making accurate turns and knowing what direction your robot is facing. We have GPS, which is very similar but more for position, so you can tell, so that your robot can tell where it is. And then we have a multifunction kind of like sensor thing that has a color sensor and a distance sensor integrated into it. Sensors, and then we can get the values for each of these sensors. Under control, you have a lot of what very standard programming uses. We have true false blocks, we have comparison blocks, we have Boolean logic, so and or not blocks, and or blocks. There should be a not block here. I think, yeah, there's not equal to block here. We have an if block, and the if block is cool because it can you can like add in more else if blocks and more else's, which is helpful for state machines. Control. Okay. We also have switch case blocks, looping blocks. So we have the very simple repeat number, so we can repeat something 2, 3, or 4 times. We have while loops, for loops, and the normal break and continues that is found in most standard programming languages. We also have the functionality to deal with arrays, or as Python and Blockly calls it, lists. So we can create empty lists, we can create lists that already have items in them. We can deal with the variables in the lists and index them properly. Math section is pretty simple. It's just numbers and arithmetic operations, absolute value, modulus, and rounding. The camera is an interesting thing in Weebots. It's you can do full like computer vision stuff in the text-based for Weebots. As far as Blockly goes, Weebots has this really cool thing called recognition object. Can anybody else see the screen? I believe I'm screen sharing the I'm screen sharing that. Okay, I'm sharing screen sharing. Okay. Okay, I won't go through the whole thing again. But again, so we have variable stuff. We can add functions. We can interact with motors. We can interact with the time that the Weebot simulation is running on. We can get data from sensors. We have standard control blocks like if blocks, conditionals, Boolean logic, and loops. We can interact with arrays, which they call lists in Python and Blockly. Math is just arithmetic operations and plugging in numbers. Camera has the ability to deal with what Weebots calls recognition objects, and recognition objects are how you can assign an object in Weebots what's called a recognition color, and so the camera students don't have to deal with full computer vision algorithms like OpenCV, which can get pretty difficult for new programmers. But these recognition objects are an easy way for students to interface with the camera and detect stuff. And then there's a lot of debugging stuff. We have quotes for printing, and also this start block, which is actually pretty important. Okay, so the start block. Okay, so something else that's really cool about Weebots, Blockly, is that it shows the text output. So this is really beneficial because students can use this tool to figure out how to go from block-based coding interfaces to more of a text-based. To a text-based. So for example, we can see out here that this start block plugs in a bunch of code that initializes the robot and gets defines some functions for color and gyroscope stuff for getting encoders. So that's all really cool. And then there's standard printing tools. Okay, so let me do this. Let me set up this screen share better so that we don't have to deal with this again. Okay. Okay, so right now I'm sharing this, and then I'm sharing this. Okay, cool. And now I'm sharing this. Awesome. Okay. So so as a demonstration of how Blockly works, I'm going to kind of go through real quick how to write a very simple line tracing program, just a normal one-eye line tracing. So in case anybody hasn't seen the algorithm for line tracing, I'll go over it real quick, 1 second. So okay, so the way this works is okay, so the way this works is if we have a robot on a black line and we have our sensor here. So right now the sensor is currently seeing a black line. So with one-eye line tracing, it's very simple to just say that if the robot sees this one line, have the left motor go forward at some speed and have the right motor stop. So what will end up happening is the robot will turn and move in this direction. And then the robot will see a white point here, at which point the robot will detect that, okay, I'm on white, it's time to turn the other way. So the left motor will stop and the right motor will go forward, and it'll cause the robot to go this way. And so in this like back and forth motion, the robot's able to trace the whole line. So it looks kind of jittery, but this is about the best that's possible with just one eye line tracing. So let me hear that. Okay, so let me demonstrate how to. Okay, cool. So let's go a little bit over how to actually how to write this program to kind of demonstrate how blockly can work. So let me switch to, okay, so the first thing that's necessary in every blockly program is a start block. And the start block, as we saw before, puts in a lot of initialization code that's very important. So from here, let's initialize our motors and sensors. So we do this by going to the motors tab and dragging over a set of motor block. We don't want it to be called motor obj. We want to give the motors good names. So I'm going to rename this to left motor. And so this set of motor, it needs to be the same as what Weebox called its motor, so that the code can match up the robot with the controller. So in Weebox, it's left space wheel and right space wheel. So left wheel, and then we're going to drag over another set of motor block, and this is going to be right motor, left motor, right wheel. Okay, cool. So from here, we should also set up our color sensor that we have. So color, we're going to do this one. So again, we want to rename this to something good. So I'm going to call this color sensor. And it's going to be a color sensor, yes. And I believe Weebox calls this color sensor. Awesome. Okay, at this point, it's good practice to add a time step so that the Weebox can process that all this stuff actually exists. So I'm going to put in time and my robot.step, and I'm going to plug in 1. So what this will do is it'll let the robot time step 1 step in advance. Okay. Okay, so after this, we do need to basically now write our very simple line tracing algorithm. Right. Okay. Let's okay. So the first thing that we should probably do is test that everything is set up right. So let me make a while true loop. So in this control section, I'm going to find this while block. And I'm going to, in this section, find a true block. So while true, I'm going to set our motors to go forward to make sure that the robot can actually move. So I'm going to set the velocity of the motor to like 20%. And then I can right click on this, duplicate it for the right motor. Okay, so now that we've set the velocity, I also want to display what value the color sensor is reading so that we know what kind of threshold, what range that we want for our line tracing program. So so in sensors, in the other section, we're going to print, which is just going to display out to the console, print get gray. So this is going to get a grayscale value on the scale from 0 to 255, and color sensor. Okay. Cool. Okay, so let's see what this does. So to run the program, we first have to click the save button. And what the save button is going to do is it's going to take this code and I think it stores it as an XML file format. It saves it locally somewhere so that everybody, so that you can access it later. And then the submit button does a very important job of converting all this to text-based code and saving it as the Python controller so that Weebox can understand it. Okay, so now on the Weebox side, what we always have to do is we have to reset the world. And this kind of puts in that Python code into the robot. And then if we hit play, to do it sometimes multiple times. Okay, cool. If we hit play, so our robot is going forward now, and it's printing that it's seeing a black grayscale value of about 143. On the top left corner here, you can see exactly what the robot's seeing. And okay, now we saw that it passed over this black line here. And while it got to the black line, it got to a minimum of around 67 or so, but it hovered around the 70-ish value. So we need to pick a good value between the minimum and the maximum, and the good value is usually around the middle. So if we go between 60 and 100, a good middle value might be, between 60 and 200. So a good value might be around 130 or so as a threshold for determining between black and white. So we go back to our code. So if we go back to our code, we can get rid of this. We know that we want a value of about 130. So now we can put in our determination between left and right to figure out which direction the robot should go. So I'm going to go into the control section, drag over an if block, and now we want to say if the get gray value of the sensor is greater than the threshold value we picked, right? That would mean it's white. So if control, I'm going to drag over this comparator block. If sensors get gray, if the color sensor get gray is greater than equal to the value that we picked, which is about 130. So we said if it's on the white, we want our robot to turn a little bit to the left, right? So we're going to set our motor velocities. I'm going to set my motor velocity. The left motor is going to stay at 0 because it's not going to move. And the right motor is going to move. So I'm going to set this at a speed of like 20. Should be good. And now we can drag in an else block here. So if we click this little gear icon, we can drag over an else. And you can see that it mutates the block and adds a new section to it. So left motor, right motor. Okay. So let's duplicate this. This time we want our left motor to move. I'm going to go 20. And our right motor is going to stay at 0. And so now this robot, in theory, when it hits black, it should turn to the right. And when it hits white, it's going to turn to the left. Okay. So close this. Now let me go through this again. So it's save and then submit. Let's see if this works. So we're going to reset and hit play. Try that one more time. Okay, cool. So it's a little jittery, but you can see that this is about what happens with a one-eye line tracing. So you can see that the robot is going back and forth between the black and the white. If I run this faster, let's see if it can. Yeah, no, my computer is not very powerful enough for this. Okay. Okay, so while we're waiting for this, does anybody have any questions so far on what I've talked about, on the code, on the interface, anything? Any questions so far? Okay. Cool. So, okay, great. So you can see that this robot is able to trace the line pretty adequately. And so there's a lot of more functions that I didn't go over with this. So the color sensor can actually detect color as well. So using it outputs a red, green, and blue value that you can use to analyze colors. So you can have the robot stop on red, which is a common task that I ask most of my students to do. Stop on red. There are distance sensors that you can add to detect obstacles. There's a gyro sensor and there's a GPS sensor to tell where the robot is and how it's which direction it's facing. So there's a lot of possibilities for this. Okay, cool. So let me go back to the slides. Okay, so so in conclusion, simulation robotics has a very strong future for remote instruction, especially for those without access to hardware. And the cool thing is that students can use unique tools. So Weebox has a LiDAR sensor and a GPS sensor. Both of these are tools that it's usually hard for students to get a hold of and how to and actually be able to use. So the fact that students can use this for simulation is really cool. It's good for building a strong computer science or an algorithmic foundation before students move on to the physical robot. So for example, if somebody is doing like a rescue line competition, they can deal with just the software getting the algorithm of their code right, of their code perfect, before moving on to the physical robot, because in the physical world, it's not deterministic, like I was talking about before, right? There's a lot of issues, there's some noise in the world, there's sensors don't always work perfectly, And for somebody who wants to focus on the software of it, it's really frustrating to have to deal with hardware issues and not knowing if your code is an issue or if the hardware is giving you an issue. So software is really good for that. Simulation is good for that. And this is especially used in like very large scale projects. So the software developers can work independently of the mechanical engineers developing robots. So for example, like I was talking about before with the Mars rover or if anybody's seen the Boston Dynamics robots, the four-legged like dog ones that walk around, jump around, they use simulation software because they need the software people to be able to work without having to worry about hardware issues. Okay, so and then a little bit about the future of where I'm planning to take this. So this is going to be used for the RoboCup Junior 2023 United States competition, as like a trial demo league. So when we get a lot of students to work with this, hopefully it'll become more mainstream, and that's really cool. As far as features that I want to add into this, it would be really cool to be able to have students embed their own custom text-based or Python code into the blocks. And so that way they will be able to learn how to write text-based code without and being while still being able to use the Blockly code as more of a flowchart kind of thing, right? They can use Blockly. Yeah, cool. That they can use Blockly as a flowchart and an organization tool rather than just actually writing all their code in it. So okay, cool. So if anybody has any questions, now's the time. So I got a question. Are there any pre-requirements for the competition? So this is really good for beginners because you don't need to know how to write text-based code. The Blockly is very self-explanatory of how it's working, and I'm also going to be releasing a lot of video tutorials. So this Blockly is a really good foundational step, and you really don't need any pre-requirements other than being able to use a computer. There aren't really any pre-requirements because students can actually just learn how to code using this and while solving an actual real world problem, right? Because this is applications in rescue robots that can go into places that humans don't have, that it's not safe for humans to go into. So students can learn to write code, have a good problem solving mindset without actually needing to write code, without needing to know how to write code before they start. Okay, are there any other questions? Okay. Okay, so if there aren't any other questions, I'm going to hang around here until 1:30. So if anybody has any questions or anything that they'd like to talk about, I'm definitely here. But I think that's about all I have. Okay, so good question. So how long does it take to learn all this? So I've been teaching this for a while now, and to get started to run the very basic program that I just showed you, the line tracing program, it maybe takes a couple of hours. It's not hard to download, install, and learn how to get started with it very quickly. And especially with the video tutorials I'll be releasing, it's going to be very easy to get started and get started picking up with this. But the cool thing is that it can also be very challenging. So for example, the green square intersection that I was talking about a couple slides here. So if you see on the bottom right, this can be kind of tricky for a Weebot's for a Blockly coder to do. But the video demo that I showed the student who was able to do all this, he was done in doing 2 hours every week for 10 weeks. So he did all that in 20 hours, which is really cool. So start to finish, learning how to use Weebots, how to put in new sensors, how to deal with all the debugging, everything included. He did all that. He did his first rescue line map in about 20 hours or so, which I think is much faster than people usually do. Oh, okay, right. So if you've done a line follower activity before this, then you even have a head start of knowing how to get your head around it. So that is really cool. Nice. So I don't think I had anything else to add, so I'll hang on here until 1:30. But I think we're about good. So if anybody has any questions, please feel free to ask. But I think we're good for today. Thank you guys actually so much for coming. I hope you had a good time. I hope you learned something. Um, and keep a watch on that dev link that I posted, because any updates to any video tutorials I had or anything will be posted on that link. So in case anybody doesn't have the link, oh, that's the wrong link. Uh, so this is the dev link. If anybody was interested in this, please feel free to keep keep checking on that. The video tutorials will be posted up there. How do you join the competition? Okay, cool. So if you're right now a starting robots student, talk to your instructor or talk to Miss Mabry. They will be able to help you get started joining the competition. So I believe in this coming year of the RCJ competition, this will be run as a trial thing. So I think your instructor or Miss Mabry would have details on that of how to join the competition. You just join it like a normal RoboCup Junior. And yes, this webinar is being recorded. So I will yeah. So once it's done, we'll send you guys the recording. And I'll be making more detailed video tutorials soon.